The more we delve into the universe, the more mysteries it unveils to us. Gravity, the invisible force that unites the cosmos, may not be as immutable as we thought. From ancient civilizations to the revolutionary discoveries of Einstein, our understanding of gravity has constantly evolved. However, recent discoveries suggest there could be a large-scale cosmic failure, a deviation in the force governing galaxies and stars. Ancient scientists reflected on the nature of gravity, laying the foundations for Newton's elegant laws, but it was Einstein, in the early 20th century, who changed our perception. His theory of general relativity describes gravity not as a force, but as the curvature of space-time. Despite its success in predicting phenomena like black holes and gravitational waves, Einstein's theory has limitations. When we turn our gaze to the scale of galaxy clusters and beyond, we find inconsistencies. Gravity seems to weaken slightly over billions of light years, and this phenomenon is what researchers now call a cosmic failure. This anomaly could point to new physics, perhaps extending the standard cosmological model to include a variable gravitational constant. Such a modification could reconcile these inconsistencies without overturning the established successes of general relativity. The discovery of a cosmic failure forces us to rethink our understanding of gravity. Could this be the first clue to a new puzzle that ultimately leads us to a theory unifying the fundamental forces of nature? Music. Long before the scientific revolution, ancient civilizations had already encountered the concept of gravity, although they understood it in very different ways. The Greeks, for example, believed in the geocentric model, where Earth was the center of the universe. Aristotle argued that objects fall toward their natural place, and this theory dominated Western thought for centuries. In ancient India, the Hindu scriptures describe the concept of gravity as an inherent force that attracts objects to Earth. Similarly, the Chinese philosopher Mozi, in the 4th century A.C., suggested that objects fall due to the Earth's force. 4th century A.C. suggested that objects fall due to the force of the Earth's energy. These early ideas, though primitive by modern standards, laid the groundwork for future scientific research. It was not until the Renaissance that a more accurate understanding emerged. The work of Copernicus, Galileo, and Kepler challenged Aristotelian views, paving the way for Isaac Newton's work. Newton's formulation of universal gravitation in the 17th century was a monumental leap. He described gravity as the force that attracts two bodies to each other, in proportion to their masses and inversely proportional to the square of the distance between them. This elegant equation united heaven and earth under a single law. In the early 20th century, Albert Einstein revolutionized our understanding of gravity by proposing the general theory of relativity, which described gravity not as a force, but as a curvature of space-time caused by mass and energy. Einstein's equations suggest that massive objects, such as stars and planets, deform the fabric of space-time, creating what we perceive as gravity. This concept was visually confirmed during the solar eclipse of 1919 in an expedition led by Sir Arthur Eddington. By observing the curvature of the light of the stars around the Sun, Eddington provided one of the first experimental confirmations of general relativity. Consider this almost a century ago. Einstein added an adjustment factor to his equations to fit the then accepted idea of a static universe, and later called this factor his biggest mistake. However, this lambda constant reappeared years later to explain the accelerated expansion of the universe. Einstein's theory also predicted phenomena, such as black holes and gravitational waves, which we have only begun to observe in recent years, further confirming the validity of his theory. The image of the event horizon of a black hole taken by the telescope of a black hole in 2019 and the detection of gravitational waves by LIGO in 2015 were monumental achievements in modern astrophysics. However, despite its successes, general relativity has limitations, as it is incompatible with quantum mechanics, the basis for understanding the subatomic world. This has led scientists to seek a more complete theory unifying these two pillars of physics in the quest to understand the universe. Scientists have discovered anomalies that challenge our generally accepted understanding of gravity. These inconsistencies indicate that our current theories, though solid, may be incomplete. The general theory of relativity proposed by Albert Einstein has become a cornerstone of modern physics. The theory has been remarkably successful in explaining a wide range of phenomena, from planetary orbits to the behavior of light around massive objects. However, recent research points to possible inconsistencies when general relativity is applied at cosmic scales. Recent research by Robin Yuen and colleagues in 2024 raised the hypothesis of a cosmic anomaly in gravity. Their research suggests that the gravitational constant might not be exactly constant over vast cosmic distances. In particular, gravity appears about 1% weaker when dealing with distances of billions of light years. This anomaly hinders our understanding of what is happening, as it implies a deviation from Einstein's theory on extreme scales. To solve this, scientists propose modifying the standard cosmological model known as lambda cold dark matter. This adaptation involves adding a new parameter that slightly corrects the gravitational constant on a cosmic scale without affecting its proven precision on smaller scales. The conflict between general relativity and quantum mechanics further complicates our understanding of gravity. The general relativity describes better the large-scale structures, such as the galaxies and the black holes, while the quantum mechanics provides the best framework to understand the particles at the smallest scales. However, these two theories are fundamentally incompatible. One of the most striking tests of this contradiction is the behavior of black holes. The general theory of relativity predicts the existence of singularities, points of infinite density at the center of black holes. On the contrary, quantum mechanics suggests that such infinites cannot exist, indicating the necessity for a new theory that can unify the two systems. Recent technological advances, such as precise measurements of the cosmic microwave background by satellites, have provided new data that either confirm or refute existing theories. These observations have led to the discovery of the Hubble tension, a significant discrepancy between the observed and predicted expansion rate of the universe. The Hubble contradiction suggests that either our understanding of the early universe or the nature of dark matter and gravity must be revised. The theory of cosmic failure, which introduces a small change in the gravitational constant, offers one possible solution to this problem. In addition, the detection of gravitational waves by the LIGO and Virgo collaborations has opened new possibilities for testing gravitational theories. These observations provide an opportunity to observe the universe in a new way, potentially revealing deviations from general relativity that could not previously be detected. The intersection of these anomalies with the predictions of quantum mechanics could lead to revolutionary discoveries. The experiments carried out at CERN, in the Large Hadron Collider, aim to explore the limits between these two realms, looking for tests that can bridge the gap between general relativity and quantum mechanics. In search of an understanding of gravitation, some scientists suggest that it may not be a fundamental force, but rather an emergent phenomenon arising from deeper principles. This idea does not contradict traditional ideas about gravitation, but rather opens new avenues for theoretical investigation. A well-known alternative is modified Newtonian dynamics, or MOND, proposed by Mordechai Milgrom in the early 1980s. The theory suggests that Newton's laws need adjustments at the very low accelerations characteristic of the outskirts of galaxies. According to MOND, these changes can explain the rotation curves observed in galaxies without involving dark matter. MOND has had some success in predicting the behavior of stars and galaxies, where traditional theories of gravity fail. However, it is incapable of explaining large-scale cosmic phenomena, such as clusters of galaxies and the cosmic microwave background, where dark matter remains a more acceptable explanation. Another interesting theory is emergent gravity, proposed by Eric Verland in 2010. Verland suggests that gravity is not a fundamental interaction, but rather arises from the thermodynamic principles of information storage and holographic screens. From this point of view, the universe can be described as a hologram where gravity arises from the changes and the entropy associated with the information stored in these screens. To simplify, imagine the universe as a giant laboratory in which books, which contain information, are stored on shelves, which are holographic screens. The arrangement and number of books change with time, which affects the general structure and creates what we consider gravity. The emergent gravity of Berlin. The emergent gravity has intriguing implications for our understanding of the dark matter. Instead of invisible particles, the effects attributed to dark matter could be a consequence of the emergent properties of space-time itself. This theory allows us to take a new look at the connection between gravitation and thermodynamics. In addition to the theories of Mond and Verland, there are several other alternative approaches. One of these theories is modified gravity, or simply MOG, proposed by John Moffat, which introduces additional gravitational fields to explain the rotation curves of galaxies and the dynamics of galactic clusters without dark matter. MOG suggests that these additional fields modify the force of gravity at different scales. In addition, the concept of entropic gravity, closely related to the ideas of Varon, suggests that gravity arises from the tendency of the systems to increase the entropy. This thermodynamic interpretation is consistent with the principles of statistical mechanics and provides a new lens through which gravitational interactions can be viewed. These alternative theories, although not universally recognized, open new perspectives for us and require further investigation and experiments. They force us to reconsider the vision of gravity not as a force inherent in nature, but as a consequence of deeper, fundamental principles. As we move toward the middle of the 21st century, our search to understand gravity continues, expanding the limits of technology and knowledge. Cutting-edge experiments and missions are being designed to test the limits of our gravitational theories, which will provide us with new knowledge and potentially revolutionary discoveries. One of the most important projects in progress is, of course, the acclaimed James Webb Space Telescope, JWST. The observations made to date have been crucial for testing theories of gravity on a large scale, especially those that predict deviations from general relativity. Another key player in gravitational research is the Large Hadron Collider at CERN. This particle accelerator, the largest and most powerful in the world, collides protons at unprecedented energies. These collisions allow physicists to study fundamental particles and forces, including the possible discovery of particles that can mediate the gravitational interaction on a quantum scale. The LHC experiments are fundamental to understanding how gravity can be combined with other fundamental forces. Space missions, such as the LISA Space Interferometer, are also glimpsed on the horizon, with its launch plan for the mid-2030s. LISA will be formed by 3 spacecraft that will form a gigantic triangular interferometer in space. This installation will detect gravitational waves with much greater sensitivity than existing terrestrial detectors, such as LIGO and Virgo. The objective of LISA is to observe gravitational waves coming from the fusion of supermassive black holes, which will test the general theory of relativity of Einstein and will provide new knowledge about the dark matter and the dark energy. But getting closer to home, the Event Horizon Telescope continues making revolutionary contributions. In 2019, the EHT obtained the first image in history of the black hole M87, which demonstrated the power of synchronizing telescopes from all over the world to create an interferometer the size of an airplane. The EHT is now focused on even more precise observations of black holes, including the one located in the center of our galaxy, Sagittarius A star. These observations will test the predictions of general relativity in extreme gravitational fields. In addition, let us remember the recent study, mentioned previously and carried out by Wen et al., which proposes a cosmic anomaly in gravity, suggesting that the gravitational constant may vary along cosmic distances. This study will be tested using data from the Planck satellite and future experiments on the cosmic microwave background. The next missions, such as the Simons Observatory and CMB-S4, aim to make more precise measurements of the CBB that can confirm or refute the existence of said anomaly, which would offer a deeper understanding of the nature of gravity to the greatest. In addition, the Rubin Observatory, RUIN, which will soon be fully operational, will carry out the legacy survey of space and time. This study will map billions of galaxies, providing a detailed view of the universe's structure and evolution. The LSSD data will help test theories about dark matter, dark energy, and gravity, and possibly reveal new phenomena that will change our current understanding. Another exciting frontier is the search for quantum gravity through lab experiments. These experiments use highly sensitive equipment to detect small gravitational effects on very small scales, where quantum mechanics effects become significant. These experiments are designed to bridge the gap between general relativity and quantum mechanics, which could lead to a unified theory of gravity. These cutting-edge experiments and missions represent the latest in gravitational research. They are designed not only to test existing theories, but also to discover new phenomena that could revolutionize our understanding of the universe. Revising our understanding of gravity could have profound implications for cosmology, astrophysics, and even technology. The anomalies and alternative theories that we have studied suggest that our understanding of gravity is far from complete. As our models improve, we can expect significant advances in several key areas of cosmology. A more accurate model of gravity could solve existing mysteries, such as the nature of dark matter and dark energy. If gravity behaves differently across vast cosmic distances, it could provide a new explanation for the accelerated expansion of the universe and galaxy distribution. This could lead to a unified model of the cosmos that better integrates general relativity with quantum mechanics. For astrophysics, improved gravitational theories can improve our understanding of black holes, neutron stars, and other extreme environments by accurately describing the behavior of matter under the influence of intense gravitational fields. We can better understand the life cycle of stars and the dynamics within galaxies. This knowledge could even reveal new types of astrophysical objects or phenomena. Technological advances in understanding gravity will undoubtedly drive innovation in various fields. For example, accurate measurements of gravitational waves can improve navigation systems and geophysical research. In addition, advances in quantum gravity could lead to new technologies based on quantum information and communication, revolutionizing computing and data transmission. Let us imagine a future in which our understanding of gravity allows ultra-precise space-time sensors that lead to the development of autonomous vehicles, precision agriculture, and disaster prediction systems. As we await the launch of new missions, projects, and discoveries, the anticipation grows. Each step forward brings us closer to unraveling the mysteries of the universe, promising a future in which our understanding of gravity and the cosmos is richer and deeper than ever. Surely you've already heard about black holes, which can be so massive that they eclipse entire galaxies, but some are so mobile that they wander through the Milky Way like cosmic ghosts, undetectable, of course. Perhaps you are confused or even fascinated by the fact that the black hole closest to Earth is not as far away as you think, and that when these cosmic giants collide, they generate frequencies as unique as fingerprints, frequencies that could be the key to unlocking the deepest mysteries of the universe. But did you know that these waves interact in a much more complex way than we had imagined? Prepare for an extraordinary journey as we delve into the mysteries of black holes, the truly enigmatic titans of the universe. In a cosmic pattern, black holes are weavers of riddles and paradoxes. Although we are familiar with small black holes, the remains of dying stars, and the supermassive ones that lurk in the heart of galaxies, there is an enigmatic class that escapes our telescopic gaze: intermediate mass black holes. The Hubble Space Telescope, our eye in the sky, recently focused its attention on Messier 4, the closest globular cluster to Earth. What it discovered was nothing short of revolutionary: a black hole with a mass approximately 800 times greater than that of our Sun. This celestial object is located at a distance of between 6,000 and 7,200 light-years from us. Why is this so important? Well, for years, astronomers have struggled with a gap in the black hole family tree. We had evidence of both the existence of small black holes with a few times the mass of our Sun and supermassive black holes with masses of millions or billions of solar masses. But intermediate mass black holes turn out to be the missing link, mysterious relatives that everyone has heard of, but no one has seen. An equally interesting question is how these intermediate mass black holes form. One theory suggests that they could be the nuclei of dwarf galaxies that lost their brightest stars when merging with larger galaxies. Another theory states that they could form from the collision and fusion of smaller black holes. Identifying these elusive black holes is no easy task, as it requires a symphony of scientific instruments, from X-ray observatories to precise calculations based on the movement of surrounding stars. The Hubble Space Telescope, with its unprecedented resolution, has played a key role in this discovery. The presence of a black hole affects its cosmic environment. By studying the gravitational choreography of the stars orbiting this massive object, scientists have been able to estimate its mass. It is like understanding the character of an invisible puppeteer by observing the puppets dance. The discovery of intermediate mass black holes could rewrite the cosmic narrative. They could be key players in the formation of galaxies and even contain clues about the mysterious dark matter that makes up most of the universe. In a cosmic world where distances are often incomprehensible, the term neighbor takes on new meaning. While our closest celestial neighbor, the Moon, is only 238,857 miles away, our nearest neighbor, the black hole Gaia BH1, is thousands of light years from Earth. But what does that proximity mean for black holes, and why is it important in 2020? The European Southern Observatory, ESO, made headlines when it announced the discovery of a black hole in the HR 6819 system, only 1,000 light years away, which would make it the closest black hole to Earth. However, this claim was later refuted by subsequent research by Abigail Frost of the University of Leuven in Belgium, revealing that HR 6819 does not contain a black hole, but rather a double star system in which one star absorbs the mass of the other, a process known as stellar vampirism. This discovery was more than just a simple correction, as it opened new possibilities for studying stellar evolution and interactions after the ejection of HR 6819. The title of closest black hole to Earth then passed to Gaia BH1. This black hole was discovered by the Gaia Space Observatory, a mission of the European Space Agency, ESA. Gaia's main task is to map the Milky Way in unprecedented detail, and it was thanks to this meticulous work that Gaia BH1 was discovered as the closest black hole to Earth. Gaia BH1 offers a unique opportunity for scientific observation and research. Its relative proximity allows for more detailed measurements and can help answer fundamental questions about the properties of black holes, such as their mass, rotation, and behavior near event horizons. The study of black holes like Gaia BH1 relies on various observational instruments, from X-ray observatories to radio telescopes. Each instrument represents a piece of the puzzle. The closer a black hole is, the more precise these instruments can be to measure its properties, offering a more complete picture of these mysterious objects. Beyond its scientific importance, the idea of a nearby black hole captivates the public's imagination, makes the cosmos more personal, and provides a tangible focus for outreach and education. The story of Gaia BH1 can serve as a gateway to astronomy and astrophysics, enriching our collective understanding of the universe. In the cosmic theater, black holes often play the role of mysterious villains lurking in the center of galaxies or in double star systems. But what happens when a black hole is left wandering alone through the universe, unconnected to any star or galaxy? What makes these black holes become rebels, and how do astronomers manage to find such elusive objects? Let's delve into the mysterious world of wandering black holes. The scientific community was thrilled when astronomers announced the first unequivocal discovery of a wandering black hole located 5,000 light years from Earth. This black hole weighs 71 times the mass of our Sun and moves at an astonishing speed of about 28 m per second. The key to this revolutionary discovery lies in a phenomenon predicted by Einstein's general theory of relativity, known as gravitational lens. When a massive object, such as a black hole, passes in front of a star in the background, its intense gravitational field deflects the light from that star. This creates a brief brightening, which is how this wandering black hole was discovered. As we know, the birth of a wandering black hole is a dramatic event. When a massive star exhausts its nuclear fuel, its core collapses and causes a supernova explosion. The energy release can be so enormous that it ejects the newly born black hole from its stellar cradle, sending it on an endless journey through space. This is probably how our newly discovered wandering black hole began its cosmic odyssey. What is even more intriguing is the speed at which this wandering black hole travels. Its speed is about 28 meters per second, which is a very high value in relation to the nearest star. This speed is probably the result of the impact from a dying massive star that sent it on a solitary journey. The discovery of this solitary black hole is only the tip of the iceberg in future missions, such as the Geotelescope of the European Space Agency, and the Nancy Grace Roman Space Telescope of NASA. Astronomers hope to find even more space travelers of this type. These future discoveries will not only increase the number of known wandering black holes, but will also refine our theories about their properties and frequency. Each galaxy is like a cosmic dance floor where stars, gas, and dust swirl in complex choreography. At the center of this dance is a supermassive black hole that sets the rhythm and tempo for the entire galaxy. Research published in the monthly journal notices of the Royal Astronomical Society shows that galaxies and their central black holes grow together regardless of their location in the universe. Astronomers have long been puzzled by the relationship between a galaxy's mass and its central black hole. Both seem to be aware of each other, even though the black hole is much smaller than the galaxy it resides in. This relationship implies a deep cosmic connection, a kind of cosmic codependency in which the growth of one affects the other. One of the most intriguing questions in astronomy is which came first, the galaxy or its central black hole. The answer remains difficult to determine. However, what is clear is that a close connection was established very quickly on a cosmic scale, paving the way for complex interaction between growth and evolution. Delve into the young, gas-rich galaxies, the cradle of giant black holes. These galaxies are like cosmic nurseries packed with the raw materials needed for star formation and black hole growth. Studies show that these galaxies, known as blue nuggets, have exceptionally high star formation rates. They feed on nearby gas streams that not only accelerate star formation, but also contribute to the rapid growth of their central black holes. When black holes feed, they become active. The gas around them heats up and emits powerful waves of radiation. This heated gas is less likely to collide with the black hole, creating a feedback loop that stabilizes the size of the black hole. However, as the galaxy grows, it can push more gas towards the center, allowing the black hole to feed and grow again. The relationship between galaxies and their black holes adjusts itself. If a black hole is too large for its galaxy, it grows more slowly, and if it is too small, it catches up due to the abundance of gas and dust within the galaxy. Therefore, some galaxies defy the norm. These blue nuggets, despite their small size, have exceptionally large central black holes. As these galaxies age, their star formation stops and they become red nuggets, retaining their enormous black holes. As we delve into the abyss of the black hole, it becomes clear that young, gas-rich galaxies serve as the birthplace of various phenomena related to black holes. Whether they are luminous black holes, intermediate mass wandering black holes rushing through space, or the black holes closest to Earth, their origins often go back to these bright young galaxies. Understanding the cradle of these giants helps us reveal the mysteries that black holes hold. Now let's see something really rare. There is a situation in which black holes collide, and by doing so, create a cosmic symphony of gravitational waves around them that vibrate in the very fabric of space-time. These waves, first detected by the Laser Interferometry Gravitational Wave Observatory in 2015, opened a new frontier in astronomy. However, recent research shows that these waves interact in complex ways as they propagate, testing our understanding of gravity and general relativity. Traditionally, scientists have used linear models to describe these waves. However, a new study revealed nonlinear effects that show a more complex panorama, like the difference between a calm pond and rough sea. In a calm or linear pond, throwing a stone creates an isolated wave. In a rough or nonlinear sea, multiple forces interact to create complex wave patterns. When black holes collide, they emit unique frequencies or music chirps. These sounds are like individual notes in our cosmic symphony, each telling us about the properties of the colliding black holes. They offer a new way to test the limits of the general theory of relativity and may even provide clues to the nature of dark matter. Recent discoveries have shown that pairs of black holes and dwarf galaxies are on a collision course. These dwarf galaxies attract gas that feeds their black holes, causing them to grow before they merge. This process is a microcosm of the larger universe, where galaxies and their central black holes grow together. These colliding dwarf galaxies offer a vision of the early universe, which was full of similar small galaxies. Most of them ended up merging to form larger galaxies, such as our Milky Way. Understanding these processes helps us reconstruct the cosmic mystery of the formation of galaxies and black holes. As we delve into the abyss of black holes, we discover that each type, from luminous intermediate mass black holes to wandering black holes that hurtle through space, plays a unique role in this great cosmic symphony. The next generation of gravitational wave detectors will likely deepen our understanding of these cosmic phenomena, and, of course, each discovery, from the frequencies they generate to the very nature of gravity, undoubtedly adds a new level to our understanding of the universe as our telescopic eyes become sharper and computational models become more sophisticated. Who knows what other cosmic mysteries these giants of the cosmos will reveal? Imagine a single point, just a speck of light floating in an infinite sea of darkness. It is not just a random point. It is our home, Earth. But what if we told you that this point is just a fleeting moment in a cosmic panorama, so vast and complex that it defies human understanding? Imagine a night sky decorated with stars, each of which represents a sun, many of which have their own planets. Now multiply that image by 100,000 million. Even then, you'll have barely scratched the surface. Beyond our Earth, our Sun, and even our galaxy, lies a structure so vast that everything you know seems like a single thread in an unfathomable cosmic web. The human mind, itself a marvel, struggles to understand this scale. Our brains are built to understand the elevations and slopes of mountains and the immensity of the oceans. But how can we understand a structure that extends billions of light years? Today we are on a journey to explore these galactic threads, the muscles of the universe itself. We will delve into an almost incomprehensible realm where even the speed of light seems slow. Spiders weave fine but strong webs, each thread connected to the other in a complex pattern. The architects of nature create these networks to survive, capture prey, and probe the environment. Now imagine a web woven not by spiders, but by the very fabric of space and time. A web that connects galaxies, star clusters, and dark matter in a complex network. This is the cosmic web, the great architecture of our universe. Each node you see here is not a single star or planet, but an entire galaxy, a colossal cluster of billions of stars, planets, and other celestial objects bound together by gravity. But what gives this network its structure? The answer lies in something we cannot even see: dark matter. Scientists believe dark matter makes up about 27% of the universe, acting as the framework on which this network is built. Although it is invisible, we cannot even see dark matter. Scientists believe that dark matter makes up approximately 27% of the universe and acts as the framework on which this network is built. Although it is invisible, Its presence is perceived through the gravitational pull that determines the formation of galaxies and their trajectories. The cosmic web has not always been as we see it today, but it has evolved over billions of years, beginning with small density fluctuations in the early universe. These fluctuations grew, attracted by gravity, and eventually formed the majestic filaments and nodes that now one of the most impressive examples of galactic filament is the Great Wall of Hercules in the Northern Crown. This colossal structure extends over 23 billion light years, making it one of the largest known structures. Understanding this network is not just academic. It is a quest to understand our place in the universe. Are we simply an accidental byproduct of cosmic evolution, or is there a grander design in progress? Scientists use a variety of tools to study this network, from telescopes that can see distant galaxies to simulations that model dark matter. Each discovery is a piece of a puzzle, a thread of a story that spans the universe. Here is the Earth, a blue and green pearl suspended in space, a planet teeming with life, from the microscopic to the magnificent. It is easy to think of Earth as the center of everything, but in the grand scheme, it is just a speck in our solar system. The Earth is just one of the 8 planets that orbit the Sun, yet stands out for its unique capacity to harbor life. The oceans, the atmosphere, the magnetic field. All these elements exist in a delicate balance. If we move the image even further away, our entire solar system becomes a small point in one of the spiral arms of the Via Láctea, a galaxy that contains hundreds of billions of stars, each of which could contain its own planetary system. The Via Láctea is just one galaxy in a cosmic network of hundreds of billions of galaxies. Each of these galaxies is a node, a single point in this unimaginable structure. Even within our galaxy, the Earth is influenced by forces beyond its control. Dark matter, the invisible backbone of the cosmic network, shapes the galaxy's structure and, as a result, the environment that surrounds Earth. However, despite its apparent insignificance in the cosmos, the Earth is unique for one reason. It has life. It is the only known celestial body where life not only originated, but has evolved to an incredible level of diversity and complexity. Humanity's search to understand its place in the universe has led to remarkable scientific advances. Telescopes observe the most remote corners of the universe, and supercomputers simulate the cosmic network, helping to answer fundamental questions about the nature of reality. For example, look at the Sun, that ball of plasma that illuminates our sky and heats our planet. It is the reason why you can see these images, the reason why life exists on Earth. But in the context of the cosmic network, the Sun is just a node, a solitary star among countless others. Near the Sun, we find other stars, some smaller and colder, others larger and hotter. Each of these stars is like a bead on an enormous cosmic thread joined by gravity and dark matter. Our Sun is located in the Orion arm of the Via Láctea, a small spiral arm about 27,000 light-years from the galaxy's center. Even within our galaxy, it is nothing special, just one of the approximately 400,000 million stars of the great cosmic network. Stars like our Sun form complex nodes that connect larger structures, such as galaxies and clusters of galaxies. They are the building blocks, the fundamental units shaping the network. So, what fuels this celestial beacon? The answer is nuclear fusion. In the depths of the Sun, hydrogen atoms collide and fuse to form helium, releasing enormous energy. This energy not only fuels the Sun, but also balances the gravitational forces trying to compress it. This energy has far-reaching consequences. It provides Earth with the heat and light necessary for life, drives our climate systems, fuels photosynthesis, and even influences Earth's climate in the long term. Understanding the Sun is fundamental to understanding the cosmic network. Several missions have been launched, such as the Parker Solar Probe and the Solar Dynamics Observatory, to study the Sun's behavior. These missions provide information about solar cycles, magnetic fields, and even the Sun's future. Although the Sun is a vital node in the cosmic network, nourishing life on Earth and influencing our local space environment. It is just one example in a universe full of stellar diversity. Each star, regardless of its size or lifespan, plays a role in shaping the cosmic network. From the smallest red dwarfs to the massive blue giants, each star is a unique node contributing to the overall structure of the galactic filaments. Stars are often classified by their mass and brightness and represented on a graph known as the Hertzsprung-Russell diagram. This diagram shows a star's life stage and gives clues about its future destiny. Let's take, for example, a red dwarf, the most common type of star in the universe. They are small and cold stars, also called M-type stars, which typically have less than half the mass of our Sun. They compensate for their small size with their longevity, as they burn for tens or hundreds of billions of years. Red dwarfs are frugal. They convert hydrogen into helium much more slowly than larger stars do. This slow lifestyle allows them to be among the longest-lived objects in space. Now compare them to O-type stars, the rare titans of the stellar world. These stars are more than 15 times more massive than the Sun and can be 1,000,000 times brighter, but they live quickly, young and hot, often ending in spectacular supernova explosions. O-type stars dramatically end their lives, collapse under their own gravity, and then explode as supernovas. These explosions scatter elements such as carbon, oxygen, and iron into space, promoting the formation of new stars and planets. Star clusters are like cosmic nurseries, places where stars of different types are born. These clusters serve as nodes in the cosmic network, connecting different regions of the galaxy and even connecting galaxies to each other. Through filaments, computer simulations help astronomers understand how different types of stars contribute to the cosmic network. These virtual models can simulate billions of years of cosmic evolution in weeks, showing how stars serve as building blocks of larger cosmic structures. Thus, we have already discovered that stars are not eternal. They are born, live, and eventually die. The life cycle of a star is a cosmic journey that spans billions of years, a journey that plays a key role in the evolution of the universe and the structure of the cosmic network. The birth of a star is a spectacle of cosmic proportions. It begins in a nebula, a vast cloud of gas and dust. Gravity attracts these particles, which become denser and hotter until nuclear fusion ignites a new star. Once that star reaches the main sequence phase, it enters a period of relative stability. The hydrogen in the nucleus becomes helium, releasing energy that balances the gravitational forces that try to compress the star. This is the longest phase of a star's life and is where our Sun is now. But even stars like ours must face change. In about 5,000 million years, the Sun will run out of hydrogen. Its nucleus will contract, and its outer layers will expand, turning it into a red giant. This phase is the prelude to the star's final destiny. Depending on its mass, a star will have one of several endings. Stars with less mass, like our Sun, will lose their outer layers, leaving behind a white dwarf. The more massive stars can suffer a supernova explosion that will give rise to a neutron star or black hole. These deaths are not in vain. The agony of stars scatters important elements through space, elements that will become the building blocks of new stars, planets, and even life. Thus, the life and death of stars is an integral part of cosmic creation and destruction cycle. The cosmic web, from individual stars to entire galaxies, is a complex network of interconnected structures. But what unites these galaxies? What are the threads that weave the universe's complex fabric? The answer lies within galactic clusters. Galactic clusters are enormous groupings of galaxies united by gravitational force. They can contain only a few or thousands of galaxies and often extend over millions of light years. Just as dark matter plays a role in individual galaxies, it also acts as an invisible glue in galactic clusters, even if we cannot see it. See it? We know it exists, since it holds the cluster together and shapes its overall structure. Within a cluster, galaxies are not static, but are in constant motion. So some may head towards the cluster's center, while others may be on their way to its edge, under the influence of complex gravitational interactions. Sometimes, these interactions can lead to dramatic events, such as galactic collisions. When galaxies collide, their stars, gas, and dark matter merge to form a new, larger galaxy. These events are crucial for the evolution of galactic clusters and, by extension, of the cosmic web. But clusters are not the end of the story, as they often group together to form superclusters, which are among the largest known structures in the universe. These superclusters serve as main nodes of the cosmic web, connecting numerous clusters and filaments. Understanding galactic clusters is the key to unraveling the mysteries of the cosmic web, as they serve as threads that connect galaxies, forming the paths through which matter and energy flow on a cosmic scale. After studying the colossal structures of galactic clusters, the threads that weave the cosmic web, we now turn our attention to an even more mysterious phenomenon. What if there were real threads, chains of pure energy that united the fabric of the universe? These hypothetical one-dimensional defects in space-time could be the universe's loose threads, remnants of the first moments after the Big Bang. Let's imagine the universe moments after the Big Bang, in a hot and dense state of pure energy. As the universe cooled and expanded, this energy condensed into matter and structure. However, not all went well. In some regions, twists occurred that led to the formation of cosmic strings. Cosmic strings, if they existed, would be incredibly thin but incredibly dense. A string less than an inch wide could weigh as much as the Earth. They would extend across the vast expanse of the universe, perhaps even from one end to the other. Due to their enormous mass, cosmic strings would exert a strong gravitational attraction that would affect the movement of galaxies and even bend light. They could serve as cosmic highways that direct the flow of matter and energy through the universe. The search for cosmic strings continues. Scientists are using a combination of theoretical physics and observational astronomy to search for these elusive structures. If the existence of the strings is confirmed, they could become the missing links that help us understand not only how the universe is organized, but also why it is organized in this way. However, let's go back to the structures of immeasurable scale, the superclusters. They're the gravitational anchors that hold together vast networks of galaxies and clusters of galaxies. Let's imagine that we move away from our galaxy, the Via Lactea, beyond our local group of galaxies, and even beyond our local Virgo supergroup. We would find a network of superclusters, each of which contains between hundreds and thousands of individual galaxies united in a complex dance of gravity. Superclusters are unevenly distributed and form a kind of cosmic skeleton around which galaxies and clusters of galaxies are located. This skeleton gives the cosmic web the shape that defines the large-scale structure of the universe. Within superclusters, galaxies and clusters are in constant motion under the influence of the collective gravitational attraction of the entire structure. This dynamic flow of matter and energy is what keeps the cosmic web alive and constantly changing. Among the most intriguing aspects of superclusters is the presence of gravitational anomalies, such as the Great Attractor. These are regions with such a strong gravitational force that they influence the movement of the entire supercluster, acting as axes of the cosmic web. Understanding superclusters is fundamental to cosmology, as they constitute the largest laboratories for studying the expansion of the universe, the distribution of dark matter, and even the mysterious force of dark energy. Scientists estimate that the observable universe contains 2 trillion galaxies, yet what we can see represents less than 5% of it. At the edge of the precipice of cosmic knowledge, we feel humble before the scale and complexity of the universe, from the smallest particles to the largest galactic filaments. Each element is a piece of the puzzle. Here we are, a pale blue dot, a mere speck in the cosmic network. But it is from this point of view from where we have begun to unravel the deepest mysteries of the universe. Armed with telescopes capable of seeing billions of light years away, we become not only spectators, but active participants in this cosmic journey, and each new discovery is a step towards the answer to the eternal question that leads us all to reflect. What other mysteries does the universe hide that we have not yet revealed? The solar system has served as a reliable refuge for life, but someday humanity will have to leave its native Earth to continue existing. In recent decades, scientists have been desperately searching the dark depths of space for a refuge for life. So far, none of the exoplanets found has disproved the hypothesis of the singularity of life, but what if we're looking in the wrong place? Perhaps planets do not have all the answers, but their moons do. In the mystical deep space, exomoons are unlike any other satellite in the solar system. The size of our Earth, these hidden giants have an amazing characteristic. Life can be found on them many more times than on common exoplanets. Today we will immerse ourselves in the mysterious distant universe and try to discover why exomoons could someday change humanity's future. Let's go back to the beginning of exoplanet science. Since astronomy did not receive a strong boost until the mid-20th century, scientists began studying the first exoplanets only recently. The first confirmed exoplanets were recorded in 1992. It was a group of planets with a mass similar to Earth's, orbiting the pulsar PSR B 1257+2. Only 3 years later, scientists found the first planet orbiting the star 51 Pegasi, similar to our Sun. This was the birth of exoplanetary science, dedicated to studying planetary systems outside our solar system and, in addition, to searching for places where life similar to human life could arise. We did not have to wait long to find other exoplanets in our visible universe. In the following years, astronomers found several more exoplanets, until in 2009, the Kepler Space Telescope was sent to explore outer space. In just 5 years of operation, it had to wait a long time in the following years. Astronomers found several more exoplanets, until in 2009 the Kepler Space Telescope was sent to explore outer space. In just 5 years of operation, it was able to confirm about 7,115 exoplanets with sizes and conditions similar to those of Earth. Currently, we already know more than 5,500 planets outside the solar system, and it is likely that the recently sent James Webb Telescope can show us more distant planets. In addition, in 2013, scientists were able to determine the color of the planet and, a year later, record its magnetic field and, subsequently, volcanic activity. Finally, in 2018, astronomers made a new, potentially revolutionary discovery. For the first time, a possible exomoon was recorded near the planet Kepler 1625b. Although at first glance, this may not seem like such an incredible discovery, exomoons open a new chapter in modern astronomy, not only because they are novel and hitherto unexplored space objects, but also because they are potential elements for harboring life on exoplanets and on the satellites themselves. Each year, the knowledge about distant and faint exoplanets deepens, bringing scientists closer to a complete vision of the history of the universe. But how did scientists manage to confirm so many planets in such a short time, when it is impossible to take a picture of each of them? Only 69 planets have been found with images. The most popular method is the transit method, which you may already know. When an exoplanet passes in front of its central star, it becomes slightly fainter, revealing the presence of an object orbiting it. Although this method does not allow direct observation of the planet and may turn out to be just an error, it is currently the most effective method. The exploration of exoplanets plays a crucial role in all of astronomy and in the future of humanity. Exomoons, as a new chapter in exoplanet science, may have great potential for the search for extraterrestrial life. However, despite this, exosatellites are not of great interest for current research. The main problem associated with the search for these exoplanets is the difficulty in detecting them by telescope radars. Although no scientist denies that some exoplanets may have satellites, it is an extremely difficult task and, to some extent, even impossible with our current technologies. The transit method, or more precisely the method of studying the displacement of the spectrum of stars, can confirm the existence of an exoplanet, but not that of a satellite orbiting it in almost any circumstance. unless, for example, the spacecraft is in the closest possible proximity to the object of observation due to a completely insignificant change in the brightness of the star. Therefore, even the first exomoon found by Kepler, and those discovered later near the planets Kepler 1708b and Kepler 1513b, are still not considered conclusive proof of their existence. Therefore, there is the possibility that it is simply some kind of technical error during the observation, which is not so far-fetched, since subsequent observations did not yield encouraging results. However, as in the case of the giant satellite Kepler 1625b, an exomoon can be seen if it is large enough. So far, the first hypothetical exomoon could be the size of Earth and have a strange, inclined orbit like that of Triton, Neptune's moon. The enormous size of a possible moon could become one of the most important elements in the search for other moons. So currently more than 20 exomoon candidates are known, all of them gigantic, at least in the case of Kepler 1625b, whose star around which it orbits is a dying red giant. The light from Triton passing through the mirrors and structure of the telescope is diffracted, giving rise to these striking peaks emitted by the moon. Diffraction, in simple terms, is what happens when a wave, such as light, travels around the edge of an object or through a small opening. Imagine light as water waves flowing through a narrow slit in a wall. When the waves pass through the slit, they deviate in different directions instead of going straight. This propagation of waves, after passing through a hole or around an edge, is what we call diffraction. In the context of the James Webb Space Telescope and its images, diffraction spikes arise due to the way the mirrors and the telescope structure are arranged. When light from a bright object, such as a star or Triton in Neptune's images, enters the telescope,